Okay, from the previous lecture, I have informed that the formulation for the voltage drop is the design current or the line current. You multiply with the circuit resistance, okay, and then times with the cos theta minus the circuit reactance times with the sin theta. So we have others formulation for the voltage drop, which is by using the tabulated millivolt per ampere per meter values. Okay, so the voltage drop formulation by using the tabulated millivolt per ampere per meter value is tabulated millivolt per ampere per meter times with the line current or the design current, and then times with the this one is actually the length of the cable, okay, divided by 1000. So if you don't consider the power factor, then this is the formulation that we can use. If we take account of the load power factor, so normally AC circuit we have to consider the power factor, and you use the size of conductors is 16 square millimeter or less, then you can use this equation. Okay, so voltage drop equivalent to tabulated millivolt per ampere per meter times the design current times the length of the cable times cos theta, which is the power factor. Okay, this one is the power factor, and then divided by 1000 volts. Okay, so for the AC circuit, that the conductors is greater than 35 square millimeter, or say equivalent to 35 square millimeter, then you can use this equation. So voltage drop, okay, voltage drop equivalent to tabulated millivolt per ampere per meter, you times with the cos theta plus tabulated millivolt per ampere per meter times the sin theta times the line current, and then times with the length of the conductor divided by 1000. So this value of the tabulated millivolt per ampere per meter, you can refer to the tabulated table of voltage drop 17th IEE regulations. So we look at the example 2. So a 415 volt, okay, 3-phase AC circuit is wired in a 4-core armored cable to BS 5467 having XLPE insulation and aluminum conductors of this is the area, the cross-sectional area, which is 35 square millimeter. If IB is 120 amps, the length of the cable is 27 meters, and the tabulated millivolt per ampere per meter is 1.95. So what is the percentage of the voltage drop? So the solution of this example is you have to calculate first what is the voltage drop. So this voltage drop, you can calculate because there is no information about the power factor. Then you can use the equation V drop equivalence to the millivolt, okay, millivolt per ampere per meter, okay, times with the IB times with the length of the conductor, then you divide by 1000, okay, 1000 volts. So this is the equation that we use for the first solution, okay. So it gives that the millivolt per ampere per meter is 1.95. We times with the IB 120 times with the length of the cable 27 divide by 1000, then you can get the voltage drop is 6.32 volt. Then you have to calculate the percentage of the voltage drop. So percentage of the voltage drop, as we know that the voltage drop divided by the phase, voltage or the system voltage. So 415 is the V line to line. Okay, so you have to convert to the phase voltage or the phase voltage. You get 415 divided by 3. Now you have to times with the 100%. You get 2.64% for the voltage drop. Okay, and then we look on to the cable impedances. Okay, so we have to identify what is the cable impedances. So in order we want to calculate the three-phase voltage drop. So three-phase voltage drop calculations is referred to as the one-way impedance. So we have, for example, here the line of R, Y, B, and neutral. Okay, so we know that three-phase have 3 lines. Okay, and then we have the neutral lines. So we know that in cable must have the impedance. Okay, we have the R and also we have the X. Okay, this one is R, this one is X. Okay, and then this one is the source. Here is the source, and then the cable. This one is the cable, and then we go to the load. Okay, so the current will flow here from the sources to the load. This one is the current. So for the phase voltage drop, we consider that the load current is flowing one way, which is from the source to the load. Okay, that's why it is referred to as the one-way impedance. Okay, so from the source to the load, the current flow from the source to the load. That's why we consider only one-way impedance. Okay, so the ohmic cable impedances. So we have to identify what is the cable impedances. So for the resistance, the equivalent, the equation is resistance in ohms per 1000 feet divided by 1000 times with the cable length in feet. Okay, for the reactant, so reactant in ohms per 1000 feet per 1000 multiply with the cable length in feet. Okay, so how about the single phase? Okay, so single phase is you know that we have a line here, and then we have, for example, we have R and N. Okay, so the current will flow. Okay, so the current will flow from source to the load. Okay, we know this one is the source. Okay, the current will flow from the source to the load and back to the source. Okay, so this is the load current flowing for the single phase voltage drop. So thus the ohmic cable impedances are calculated as, so because of two cables, okay, the current flow for two cables, so RL equivalent to 2 times the resistance in ohms per 1000 feet divided by 1000 times cable length in feet, and then for the impedance 2 times reactant in ohms per 1000 feet divided by thousands times with the cable length in feet. So this is the example. Okay, we look at example 3. So determine the voltage drop along a 240 volt. Okay, so we know that 240 volt is the single phase branch circuit. So with 135 feet in length, okay, the length of the cable, and consisting of 10 AWG, American wire gauge. This is the standard method denoting the wire dia. the wire diameter, okay, and then THW is the thermoplastic heat and water resistant insulated wire copper conductor. So the load current is 13, okay, with angle negative 25 degree amperes. So assume the PVC conduit. So what is the solution? Okay, this is the solution. First, you have to refer to the table of uh, 6 volt cables. Okay, okay, so you have to refer to the table of 600 volt cables, and then from there you have to look at the size of the cable is 10, okay, and from this table you can get for the AC resistance for uncoated copper wires is 1.2 ohm per 1000 feet, and then you look at the reactant. This one you search at the reactance for all wires column, then you can get 0.005 ohm per 1000 feet. Okay, then you have to use the equation for the single phase. So as I mentioned before, so you have to use this equation lah. Okay, this one. Okay, so that equation is we know that R equivalent to 2 times with the R per 1000 feet. Okay, then you divide by 1000, you times with the length of the cable. Okay, so this one is referring to this one. Okay, so 2 times 1.2 per 1000, you time with the length of the cable 135, then you can get 0.324 ohms. Then for the reactance, the equation is still the same, so just substitute from the resistance to the reactant. 2 times 0.05 per 1000 times 135, you can get 0.0135 ohm. Then you use the equation for the voltage drop here. Okay, so we know that the equation is IB times R times cos theta minus X times sine theta. Okay, so you just put all the values inside the equation. Then you can get the voltage drop is 3.89 volt. So you have to calculate what is the percentage of the voltage drop. So the voltage drop, the value of voltage drop, you divide by the system voltage or the phase voltage times with the 100%, then you can get the voltage drop in the cable is 1.62%. Okay, transformer also have the voltage drop. So in this section, we will identify and determine how to calculate the voltage drop for the transformer. So three-phase transformer impedances are the elements that we have to identify first before we calculate the voltage drop. So these three-phase transformer impedances reflected to the low voltage side are given by this equation, these two equations. Okay. The first one is the resistance of the transformer. So 1/100 times with the percentage of the resistance times the secondary line voltage squared divided by the transformer volt amp rating, which is the apparent power. So for the reactance of the transformer, it's also the same equation as the resistance, but the differences is you just substitute the resistance with the percentage of the reactance. Okay, Others is almost the same. Then if in the questions it gives that the percentage of the impedance of the transformer and also the X per R ratio, then you have to use these equations in order to identify what is the resistance and the reactance of the transformer. So how get this equation is by analysis from this triangle. So we have here is the impedance, this is the resistance and also the reactance, and this is the theta. So we know that from here tangent theta is equivalent to x over r. Okay, so theta is tangent minus 1 x over r. So this is the equations. Okay, from here you can calculate what is the percentage of the resistance of a transformer by using this equation. Percentage of the impedance of a transformer times with the cos theta. This one is for the resistance, and for the reactance you just substitute the cos with the sin theta. Okay, we look at the example 4. So determine the voltage drop through a 115 kVA. This one is the apparent powers, and then we have 3300 volts for the primary side of the transformer, and then we have 415 volt star connection for the secondary side of the transformer. So three-phase transformer having an impedance of 4%. So this one is the percentage of ZTR, okay, equivalent to 4%. And then given that the X per R ratio is 1.8 and the transformer is operating at full load, 0.82 lagging power factor. So lagging shows that this is the inductive load. So the solution for this example is, first you have to identify what is the impedance angle by using the equation theta equals to tangent minus 1 x per r, and this x per r ratio has been given, which is 1.8. So theta is 60.95 degree, and then you have to calculate what is the transformer resistance and also the percentage of the reactance transformer. So this equation is referring to this two equation. Okay, so you use this equation to get the percentage of the resistance and also the percentage of the reactance of the transformer. So you just insert all the value here, and then you get for the resistance is 1.94% and for the reactance is 3.5%. And then you have to calculate what is the value for the resistance and also the reactance of the transformer by using these two equations. Okay, so these two equations, you just insert all the data, all the value, then you can get the resistance and also the reactance. So I show one only, RTR equivalent to 1 over 100. Okay, you times with the XTR. Okay, this one is the RTR percentage, and then you have to multiply with the secondary line voltage squared divided by the apparent power. So you will get the value for the RTR. Okay, for the XTR, you just substitute here percentage of the reactant of the transformer. Then the others is almost the same. Then you can get this value for the reactant and 0.02905 ohm for the resistance. And then you have to calculate what is the full load current of the transformer. Okay, so full load current transformer, you have to use this equation as equivalent to 3I V phase. Okay, as we know that V phase, okay, V phase is V line to line over cert3 for the star connection. So we just substitute this equation in this equation. So S equivalent to 3I V line to line over cert3. Okay, so we get S equivalent to cert3 I V line to line, and I equivalent to S over cert3 V line to line. So this is the equation here. Okay, then this one is the S cert3 and V line to line, which is 415 volt. Now you have to calculate what is the angle for the current. So negative cos minus 1, 0.82. You get the current for the transformer is 160 with the angle negative 34.92 degree ampere. Now you have to calculate what is the voltage drop. The voltage drop, you just use the previous equation, which is V drop equivalent to IB, okay, times with the R times cos theta minus the reactance of the transformer times sin theta. Then you can get the voltage drop, which is 8.61 volt. Okay, this is the magnitude of the voltage drop. Now you calculate what is the percentage of the voltage drop. Is you divide the magnitude of the voltage drop with the V low voltage system, which is 415 volts. You time with the 100%. Now you get 2.07 percentage, and this is the percentage of the voltage drop for the transformer.